All right. So thank you all for being here. This is going to be recitation 8 or 9, sorry. And we're going to be talking about quantization, dynamic range, discrete signal properties, and discrete Fourier transform. So first, let's start with quantization and dynamic range. So the bit resolution for an analog to digital converter is the number of bits defined as n that are used to represent each signal. It's important to note that n has to be an integer, cannot be a decimal, has to be a whole number integer. And the bit resolution is often referred to as just resolution. And the dynamic range of a system is equal to 2 to the n. That's the number of levels based on your number of bits. And your dynamic range in decibels is just 2 to the n. Take the log base 10 of that and multiply it by 20 to convert it to decibels. The signal resolution, which you can also refer to as step size, is defined as delta, and it's given by the equation below, delta equal to r over 2 to the power of n minus 1, which for many systems, and in general, if your 2 to the power of n is considerably larger than 1, you can just approximate it down to r over 2 to the power of n. And r in this case is going to be equal to your input signal range, your Vmax minus your Vmin. And then your quantization error is the difference between the analog input and the quantized output. So let's go ahead and jump into a problem. So we want to determine the minimum resolution required for an analog to digital converter handling an incoming signal ranging from -500 to 500 millivolts with a sensitivity of at least plus or minus 1 millivolt. So we jump over to my iPad quick. All right. So we wanted to determine the minimum resolution. So our resolution in this case is going to be equal to n, which is equal to our number of bits. And we want it to handle a signal ranging from -500 to 500 millivolts. So our R is going to be equal to Vmax minus Vmin, which is going to be equal to 500 millivolts minus -500 millivolts, which is going to give us 1 volt. And we need it to be sensitive to at least plus or minus 1 millivolt. So our sensitivity in this case is going to be our signal resolution. So we have sensitivity is equal to our signal resolution. So now how can we solve this for our bit resolution or our n value? So we're given the equation of step size is equal to r over 2 to the power of n minus 1. We're going to approximate that down to r over 2 to the power of n. So we're going to get step size or sensitivity is equal to r over 2 to the power of n. We need our step size or our sensitivity to be at least plus or minus 1 millivolt, which means that our signal resolution equation, so this part of the equation here, needs to be less than or equal to 1 millivolt. So we're going to plug in 1 millivolt for our sensitivity. And that has to be greater than or equal to R over 2n. All right. And now we need to solve for 2n. So we can go ahead and multiply over 2n and divide by 1 millivolt to get 2 to the power of n is greater than or equal to R over 1 millivolt. And we know that our R value is going to be 1 volt divided by 1 millivolt. And that's going to be equal to 1,000. The easiest way to calculate that is 1 volt is equal to 1,000 millivolts. And then you're just dividing by 1. So you're going to get 1,000. And we're left with 2 to the power of n is greater than or equal to 1,000. Now there's two ways to approach this problem. In this case, in the PowerPoint where the problem was defined, if y'all have it up, it provides us a list of 2 to the power of different integers up to 16. So we need the first value of n that is going to be greater than or equal to 1,000. And if you look on the PowerPoint, we can see all the powers of 2 to the power of 8 is 256. That's not greater than 1,000. To the power of 9 is 512. That's not greater than 1,000. But 2 to the power of 10 is equal to 1,024, which is greater than 1,000. So 2 to the power of 10 is equal to 1024, which is greater than our 1,000, which means our n has to be equal to 10. The other way to approach this is if you have a calculator, which you won't on your exam, but just in general, if you take log base 2 of 1,000, you get 9.96578. And whenever you take the log base 2 of your value, you always have to round up. Because if you round your number of bits down, that's going to decrease your step size. That's going to increase your step size and decrease your sensitivity. So you always have to round it up to make it more sensitive rather than round it down to make it less sensitive. Even if it's 9.01, you still have to round it up to get the correct answer. But we get n is equal to 10. And that is what it's looking for. So we were looking for the minimum resolution required. And that's going to be 10-bit resolution. Any questions on that?
For the, like we do plus minus 500, but we don't do like plus minus 1. Like, so we do like 500 minus like the min to get like 1,000 millivolts, but we don't do that for the noise or like the sensitivity or whatever. So why is that?
Yeah, so for the input signal, we want it to range from negative 500 to 500. But we want the sensitivity just to be with it under 1 millivolt. So it doesn't matter for the sensitivity if it's plus or minus 1 millivolt, because we're going to be in both the positive and the negative domains with an input signal ranging from negative 500 to 500. We just need it to be accurate within 1 millivolt. Does that kind of answer your question? Does that make sense?
Yeah, it does. But yeah, so in the examples he put on, like we did like last week on Thursday, I think it just said like flat, like a flat number. It didn't say like a plus minus.
Yeah.
So when we see that, we're just assuming that it's kind of like both ways, right?
Yeah. So it shouldn't make a difference if you define it to be sensitive to plus or minus 1 millivolt or at least 1 millivolt. It shouldn't make a difference.
Okay, cool. Thank you.
Absolutely. All right. Any other questions on this particular problem?
Yeah, so for the exam, will we be given all these powers of 2? Because you said we don't get a calculator.
Yeah, I am not positive. Amelia, do you know if that will be given on the exam?
It would mostly be given.
Okay. Yeah, I think up to the values that you need, it will be given.
Okay, perfect. Thank you.
Absolutely. All right. Anything else? Okay. So let's go ahead and jump back into the PowerPoint. So now we're going to talk about we're going to talk about LTI systems with discrete inputs. So this is almost identical to the LTI systems we did in the past with continuous signals. But let's go back over it. So we define a system as linear if it meets the scaling and additivity conditions. So the scaling condition is if the input is multiplied by a constant, the output is multiplied by the same constant. And additivity is if you do x1 plus x2 and input it into the system, it should give you the same as y1 plus y2. And that combines into alpha of x1 or t alpha of x1 n plus beta x2 of n gives you alpha y1 of n plus beta y2 of n. And then for time invariance, we're going to have a time shift in the input signal leads to a time shift in the output signal. And these are the same properties we had before. Just make sure you're still remembering these. So let's go ahead and jump into the second problem. So we wanted to determine if the following system is linear, time invariant, or both. So let me go ahead and jump into my iPad again. And again, if y'all have any questions, go ahead and interrupt me. I don't mind at all. So we're trying to determine if the following system is linear, time invariant, or both. And we're given the system y of n is equal to x of 3n. So first, let's test for linearity. And if we remember our definition, if x1 of n gives y1 of n, and x2 of n gives y2 of n, then if we input a signal of alpha x1 of n plus beta x2 of n, it should give us the output alpha y1 of n plus beta y2 of n. So let's go ahead and input x1 of n, and that's going to give us our y1 of n. And based on our system definition, that is going to be equal to x1 of 3n. And we're going to do the same for x2 of n to get y2 of n, which is going to be equal to x2 of 3n. So now we're going to define x3 of n as alpha x1 of n plus beta x2 of n. And if y3 of n is equal to alpha y1 of n plus beta y2 of n, system is linear. So we can test that. We plug in x3 of n, and we're going to get y3 of n. And that's going to be equal to x3 of 3n. And we know we defined our x3 to be alpha x1 of n plus beta x2 of n. Which is going to give us alpha x1 of 3n plus beta x2 of 3n. And as we solved up here, y1 of n is equal to x1 of 3n, and y2 of n is equal to x2 of 3n, which we can identify in our equation here. That's y1 of n, and y2 of n. And we can see that our y3 we get when we plug in x3 is equal to our value if the system is linear. So we can say this system is linear. Any questions on the linearity part? All right. Let's test for time invariance now. So, in order for the system to be time invariant, if we provide an input x of n and it gives us y of n, the system is time invariant if the input x of n minus n naught gives us an output of y of n minus n naught. So first, we have y1 of n. We plug this into our system. We get x1 of n. Plug it in. We get y1 of n, which is just going to be equal to x1 of 3n. So now we can compare our output to a shifted input. So we're going to let x2 of n be equal to x1 of n minus n naught. That's going to give us y2 of n. And then if we get y2 of n is equal to y1 of n minus n naught, the system is time invariant. So first, let's figure out what is y1 of n minus n naught. We defined what y1 of n was up here. So we simply have to apply a shift to that. So that's going to be our y1 of n minus n naught. So now let's find out what y2 of n is. What y2 of n is, if we plug in x of n is equal to x of 1 minus 1 of n minus n naught. So we do x2 of n, plug it in, we get y2 of n, which is going to be equal to x2 of 3n. And because our x2 is defined as x1 of n minus n naught, we're going to get that is equal to x1 of 3 times n minus n naught. And we can distribute that out to be x1 of 3n minus 3n naught. And we can see that our y2 of n does not equal our y1 of n minus n naught. So y2 of n does not equal y1 of n minus n naught. Therefore, we can say system is not time invariant. Any questions on that? I know we've done this in the past, but if you're confused on anything here, please ask a question. We're here to help. All right, if there are no questions, I go ahead and pass it off. If y'all have any further questions, feel free to type it in chat. Get back to you there.
Cool. Thank you, Ryan, and hello, everyone. Welcome to Recitation 9. Apart from what Ryan have just taught us about, I'm going to be talking about discrete time Fourier transform. Okay, are you ready? If we are ready, then let's go. Okay, let me share my screen. Can you see my screen okay?
Yep,
Give
we
me
can see it.
thumbs up. Cool, thank you, Ryan. Okay, let's do some recap with Fourier transform here. Anyone remember what Fourier transform is? Oh, thank you, Isabella, for the background. So when we talk about a normal Fourier transform, we usually use that with time signal, right? And then we apply Fourier transform to time signal, and we will get the signal in frequency term. And when we want to reverse from frequency terms into time signal, we use inverse Fourier transform, right? But we're quite advanced in our class now. So instead of just sticking to the same time signal, we will be talking about, sorry everyone, discrete signal. And to perform Fourier transform on discrete signal, this is when we use discrete time Fourier transform. And the thing that we will get from this is gonna be x omega. Like the omega has like resistance, okay? And that's gonna be our signal in frequency. And when we want to convert back from frequency to discrete time signal, we use inverse discrete time Fourier transform. Okay. And with this topic, you will be using most table 6.1 and 6.2. Anyone have question on this before we move forward? Okay, cool. We don't have question here. Let's jump into our question. Okay. So the question is going to be the same question on our slide here. Let's start with this question. find the discrete time Fourier transform of the following. Let's start with the first question here. Yn equal -1/2 xn plus 3. The first thing that we should do is to list the property that involve in this system, in this signal. Okay, let's look at table 6.1 here. From our question, -1.2 xn plus 3, right? Anyone would like to point to me what would be the relative property that we'll be using to solve this question? Anyone would like to try?
Linearity.
Yes, thank you, linearity. We need linearity for this question. And what else?
Time shifting.
Yes, time shifting. Thank you so much. Okay, I'm gonna take note of these two properties. I'm gonna snip this here. Okay, so since we know what's the property involved in this question, we want to merge all of them together. And for our question, it should look something like linearity, our A, right? In this case, would be -1.2. -1/2, sorry. And our K is gonna be -3. We just mark that down for now, okay? So, the discrete Fourier transform.
Just wanted to say something right here.
Yes, Professor?
So you circled minus k as -3. I think you meant k is -3, right?
Yes, K is -3. Let me make
Yeah.
that clear. Thank you, Professor, for pointing that.
Thank you.
K is -3. All right. Let's continue. The output of Yn into the discrete Fourier transform would be Y omega. And its frequency domain, which will be discrete Fourier transform of our original signal Yn, which is actually discrete time Fourier transform of -1/2 xn plus 3. And we have already identified the related property here. Therefore, the signal that we should expect to see after this discrete time Fourier transform should look like this. It should be A x omega from linearity, and because of time shifting, it should be E. This is E to the power of -j omega k. And if we plug in our value of a and k inside, we should be getting -1/2 x omega, right? A x omega, and then multiply by e to the power of -j omega and k. Our k is -3. And if I put everything nicely together, we'll get -1/2 times e to the power of 3j omega times x omega. And that would be our y omega. Right? Anyone have questions on this part? Give me thumbs up if you're cool with this. Okay, I don't think I can see the thumbs, but okay. I assume that everyone is. Oh, yes.
I was just gonna ask, so in the time shifting, there is a X with that symbol there. So do you not put that in there, or?
Oh, is the same thing here. It's the same x omega.
Oh, so you only need to put it once?
Yeah. So we merge it. We merge them together.
Oh, okay. Thank
Yeah.
you.
Oh, let's see if I can mute. Okay. Cool. For 1 hour. Cool. Okay, now let's move to the next
Also,
question.
put a parentheses over around the omega in that last line.
Oh, thank you, Teresa. Okay, cool. All right. Now, let's look at the next question. Let me add more page here. Okay. The question that we have is yn equal x -n times e to the j to n -n times e to the power of j to n. Right? Okay. Let's see what would be the property that involved in this question. Let's look at the table. Anyone would like to help me see what would be the property that I should use in this question, or the pair that I should use in this question? Tick tock, tick tock. Do you see something? Anyone would like to find that out?
I mean, there's a time reversal.
Yeah, that's an interesting point that you raised up. Yeah, because it's kind of right, but we'll approach this problem. I'll tell you the trick in like next 10 seconds. But the property that I want to point you here is the frequency shifting. It's gonna be this one, right? But the problem is that we have x -n, right? But in the property, they use xn and not negative n as we have here. Therefore, there's gonna be a trick that we're gonna use to approach this problem to make our system work with the properties on the table. But let me snip this first. Yeah, that's the right direction. Nice catch. Okay. We encounter some problem that we just pointed out earlier because we don't have xn, right? Our x is with negative n times e to the j to n. Therefore, if I want to make this seem easier in one equation, I want this and this, the n term, to have the same sign or to be the same. Therefore, I'm gonna transform a little bit. I still keep x, negative n. But what I do with this term instead, I'll pull the negative out of it, and I'll have e to the power of negative j times 2 and negative n. Do you see what we are trying to do here? So therefore, what we will have here, I'll call it as a new function, x1 of negative n. Will be the
Alpha
same
is the
thing.
reason why you're not using the time reversal property separately, because you could consider the signal as a frequency shift on the time reversed signal. So if you could call the x of minus n as x1 of n, where x1 is just a time reversal, and then apply the property to that, and then think of it as a shift to that. I like the way you're doing it, but you have to be very careful when you change variables because you need to keep track of the change variable. So it's not going to be enough to, and I'm sure you're going to do it right later on, but sometimes it's hard to track. Instead, if you just do a time reversal and pretend that the x of minus n was a new x of n, now you're applying the frequency shift to that. But anyway, please go ahead.
See, Professor. Yeah,
Yeah, go ahead
I
with
think
your way.
okay, we can try that later too. But I actually just got this from the solution note. So okay, I'll proceed with that way. But I think essentially you're right, Professor. We could use the time reversal as well. Okay, so let's recap this part. We'll call it as new variable x negative n, where this is gonna be the same thing as this one. Okay. Oh, can you hear me well, everyone? Can you still hear me, everyone?
Yep, you're all good.
Okay, thank you. Okay. And to find the discrete time Fourier transform of this signal, we will find a discrete time Fourier transform of x1 negative n, and essentially we will get x1 negative omega. You just note that down. But since we know that x1, which is another variable, x1 omega, would be discrete time Fourier transform of x1 n, which is the original signal here, right? And because we say that x1 n is equal to xn e times 2j to the power of n. Let me check something a little bit. Okay. Okay, it's still x1 of n. Yes, so when we transform into x, it will be xn, okay. Time e to the power of 2jn, okay. And let's look at the property that we just defined before. It is now in this form, right? This part is in this form already. Anyone would like to help me identify what would be our omega naught in this case? What is our omega naught? Like we already have this part, right?
Omega
And
2.
since we have- Yeah, omega naught. What would that be?
Omega 2.
You're quite right. Omega naught is actually just 2. Yeah. So yeah, you're almost right. Just 1% more. And therefore, after we apply the discrete time Fourier transform of this term, we will get x of omega minus 2, right? But this is just x1 omega. But what we want x omega. Therefore, and we know that x1 omega is when we change n to negative n, right? Now we're gonna do the same to omega. So basically we use time reversal property here. Therefore, we will get our x omega as excuse me, we actually want y omega. Therefore, we will get our y omega as x negative omega minus 2. And that will be the answer of this question. Do you have any question or comment or concern?
How would we solve this using the time reversal?
Okay, let's do it. Let's add one more page here. Okay.
Effectively, you've done it using time reversal. You just wrote it a little bit differently than I would have, but this is using time reversal since you already have your step in the middle where you say y of omega is DTFT of x1 of minus n, which is x1 of minus omega. So you are actually doing it with time reversal.
I see. Yeah, we are actually doing time reversal here. Is when we change from omega to negative omega here.
So I was a little bit confused initially, so I'm responsible for the confusion because when you started writing out as minus n and minus n, I thought you were going to do a variable shift, which you didn't. And the way you worked out is exactly what you would do for time reversal.
I see, Professor. I think I can explain this again to everyone if we're still confused. But would you like me to do that now, or should I do that after I move to next question?
Yeah, we can come back to it if there's more questions.
Yeah, I can come back if anyone is still confused on this. Okay, but now let's look at this question. We're still in discrete time Fourier transform, but instead of just doing the normal discrete time Fourier transform, this time we'll have to do the inverse Fourier transform to find xn. So we were given signal x omega, right? It's in frequency domain. And to change that into time to signal in discrete time domain, we're gonna use inverse discrete time Fourier transform. Okay, I'm gonna snip this with me. Okay, doesn't want me to copy everything. Let's say we have our x omega equal 5 over 5 minus e to the negative j omega and squared. Okay, let's look at the table. This is our x omega. Anyone would like to help me see what is the related properties or pairs to this signal that we have? I give you a hint. Look at table 6.2.
The weighted exponential? Or wait, no, sorry. Just the exponential.
Actually, you're right, because we have square, right? So it would be weighted exponential. Top one or lower one? I tricked you. It's actually lower one. It would be this one that we use.
Oh, sorry, I couldn't see because I was looking at the A times E.
Oh,
Yeah.
I see. But yeah, you got the idea, right? That's great. Because we don't have the term, the complex term here, we don't have e to the negative j omega, and we only have like integer here. We're gonna use this. And okay, when I look at this, first thing that will pop in my mind is that I have 5 in my signal, but on the property is just 1. How should I proceed this question? Anyone have any idea what I should do? Some thoughts?
Come on, guys, we did this in class today. Something similar.
We only have like one in the formula table, right? But we have 5.
Wouldn't you just divide by 5 to get 1?
Yeah, we can divide it by 5. We can do that too. So like I understand that. What you mean is to, okay, it's essentially something like that. So we will like divide it by 5 and take 5 out of the bracket. Okay, let's transform this together, everyone. If you would like to try it on your paper right now, and let's compare our result, that would be cool. Okay. And what I would do, I'll start at the lower bracket. I only have 1 there, right? So I want this term to be 1. I want from 5 in the bottom to be 1. I'll take 5 out. And what will remain in the bracket would be 1 minus 1 over 5 e to the power of negative j omega square. Right? And for the upper part, I want that to be 1.
Don't forget that the 5 is outside, so the 5 covers the first expression. You're taking 5 out of a square, so you basically have 25. So your answer is right, but you missed 1 step there.
Okay, thank you, Professor. It
But
would
your
be
answer is right. It's gonna end up 5 divided by 25, which is 1 over 5.
25.
25 there and
5
5 on top. And 5 on top.
and 5 on top. I think I figured it. Oh, actually, let's do this slowly. Okay, we have 25. Thank you for pointing out, Professor. And what I can do, I put 5 on top. Wait, it's already 5. Let's say it's 5 times 1, not just 1. And I would divide this 5 over 25 multiplied by 1 over 1 minus 1 over 5 e to the power of negative j omega square. I think someone sent something in the chat. Okay, see you later, Professor. Thanks for coming.
Bye.
Bye. Okay, and we have our 5 over 25, right? It's essentially just 1 over 5. Therefore, our thing will eventually look like this. Oh, yes, this is our x omega. Okay, we know that we needed one property for sure for weighted exponential, but since I have 1 over 5 here, it will involve linearity, right? Let me snip that too. Now we have to use what? We'll have to use linearity property as well. Wait, okay. Let me make this smaller so we have space. Okay, anyone would like to try after we have all the transform pair and property? What will my xn be? Like I have my xn here, and I know it is the inverse discrete time Fourier transform of x omega big X. And you got everything you need. You got this thing, property. You got this pair and you got this property. Okay, let's start with easiest step first. Oh yes, Isabella, you already got everything now. That's great. Beautiful. Okay. Let's do this together, shall we? We have can anyone tell me what will my A be? If you look at this. It will just be 1/5, right? Our A in this will be 1/5, and our A for linearity also be 1/5. Okay, it's this 1/5. This is gonna be this A. So if I merge all of my property together, I expect to get something that looks like I just think of this n plus, oh my god, not enough space. N plus 1 a to the power of n un, and that's for just weighted exponential. But because we have linearity, we have another a here. Be mindful that these a might not be the same, but essentially they're the same in this problem. Therefore, what we'll get is that first a 1/5 with the green arrow here, 1/5 times n plus 1 times a, which is also 1/5 as well, to the power of n and un. That would be our xn, which is signal in discrete time. Let me check with you, Isabella. Okay, we got 1/5. We got un, n plus 1. Oh yeah, I see what you do. So Isabella answered. She multiplied this term together. So that's nice, Isabella. What we will get in the end, we'll get 1/5 to the power of n plus 1. Nice, Isabella. Times n plus 1 times u of n. And that's it. Fourier transform problem. Cool. Thank you everyone for coming to recitation today. We don't have any more questions for tonight. Yeah. Do you have any question, comment, or concern about the inverse Fourier transform before I go back and show you again how to put the previous question nicely?
Could you just like run through this problem? Because I kind of got confused where you have the x omega squared.
X omega
Linearity rule. Oh, wait, never mind. That's an equal sign. Sorry.
Oh, I see. Wait, is it you mean this one? Okay. Let me draw it nicer. We write it nicer so we don't get confused. X omega. Any more question about this question? Okay, if you don't have question on this part anymore, we can go back and try to do this question again, but with time reversal priority at once. Okay. Okay. For let me take time reversal priority with me. Oh, let me skip that again. Okay. So if we merge after we identified our properties here, let's see how will our y omega will look like. So we have x negative n times e to the power of j to n. If we put in all of our properties together, we will still have x omega minus x omega naught. Can you still hear me, everyone?
Yep, you're all good.
Okay, cool. Because I just hear my earbud battery running low. Okay. Oh, I think I still got time for this. But because we have time reversal property as well, we should be having the negative sign in front of our original omega. Therefore, after the discrete time Fourier transform, and we already identify our omega not equal to, we should be getting negative omega minus 2. And this is the discrete time Fourier transform. Check. Of x negative n time e to the j 2n. This is y omega. Is it clear? Is it clear? Does it help? Do you feel this is better than the one I just did?
It's good, Alpha. Okay, cool. If you have any question, please let me know. There's only Isabella.
That's it.
Okay, then that's it for today, I guess.